Hi, I'm Gabriele. I'm a research engineer at IBM in Ireland, and this work is a collaboration between IBM Research, IBM Watson Health, and fraud, waste, and abuse investigator in the US. I'm glad to share with you some challenges and key findings of this cross-disciplinary project, which aim to learn insurance benefit rule from policy text with small label data. This work has direct impact on people's lives and society. I therefore invite you to check out the paper and the open source code. A top priority for social and healthcare system globally is to ensure that a fair distribution of healthcare funds, reduce disparity, and protect financial integrity, so that there is enough for everyone in need to get the vital health and social services they are entitled for. Therefore, the motivation behind this work is ensuring that public money goes where it's needed. In the US alone, healthcare fraud losses are estimated at tens of billions each year. These are vital health funds drained by systematic intentional fraud or unintentional waste on services unnecessary or inconsistent with medical practices. This number indicates that there is a significant opportunity for recovery of funds so that the money intended for vital public health program is not wasted. Catching provider who systematically infringe policies is a very labor-intensive and error-prone task because of the overwhelming amount of tax policies that need to be reviewed and interpreted by investigators. Most of the rules in policy don't get encoded into algorithms, and most of the fraud, waste, abuse is never surfaced. Therefore, in this work, we propose an approach that combines AI and NLP, ontology, and knowledge graph to automatically extract and convert the content of regulatory healthcare tax policy into both human-friendly and machine-consumable policy benefit rule. In a previous work, we described a deterministic approach for the extraction of benefit rule based on linguistic dependency and semantic patterns. In a first step, a classifier assesses which paragraph likely contains benefit rule. Then the system annotates domain entities and relations based on a domain ontology defined by the subject matter expert and extract functional dependency between them. The output in the form of linguistic predicate argument triples is then transformed into a consolidated semantic knowledge graph. The knowledge graph can then be mapped into an equivalent human-friendly rule. The rule, with the investigator oversight, can then be executed to identify the claims at risk. The deterministic approach for rule extraction based on the linguistic dependency and semantic patterns achieve good results. However, this approach is unable to learn from human correction, and it is also limited by the coverage of the ontology. Therefore, in this work, we propose a combination of neural and symbolic approach. One of the first advantages of the fusion of neural and symbolic approach is to implicitly learn extraction rules, avoiding to define them manually. Furthermore, the system can learn from the addition, correction of rule and identify new elements beyond the vocabulary of which the model was trained. To achieve this, a neural NLP model learn which span, namely one or more consecutive words in policy text are rule condition. For example, services that are mutually exclusive, that mean not payable when billed together. The domain ontology built with the investigator support both human understanding oversight and act as a blueprint for constructing semantically meaningful rules from the condition labeled by the neural model. For example, determining if a complete mutually exclusive rule can be formed. For each sentence, all the labels predicted by the span predictor that are compatible with the type of benefit rule are clustered. Subsequently, we identify for each cluster the entity annotation that overlaps with each label and whose type is compatible with the range of the predicted label, which correspond to a condition defined in the ontology. More specifically, the span annotation can be formalized as a span prediction problem, where a sentence S is treated as a token list, and for each token, one or more labels are associated. The set of labels correspond to the different condition types in the domain ontology, plus an additional O label, which represent token outside any annotation. Spans are then identified aggregating consecutive tokens with the same labels. A span can have more than one label. Therefore, we use a pre-trained BERT as a backbone model, and we add the multi-class classification head on top of it to enable the multi-class labeling. To train the NLP model, we use a small set of 141 benefit rules identified by professional investigators in dental policy document from 2 US states. Since annotation is an extremely expensive process and requires domain-specific knowledge, in the experiment, we analyzed 2 techniques to reduce the number of annotations required to achieve good performance. The first technique is fine-tuning the language model using the BERT standard training with domain-specific text, in this case, policy text. This helps the model capture domain-specific semantic relationship and thus make it easier to learn the multi-class classification downstream task. The second technique considers enriching the available label data using data augmentation. We propose a controlled data augmentation technique that preserves the main semantic structure of the rule, where the span are perturbed, but the label are persist. The technique consists in randomly replacing a span with another that has the same label to create new semantically similar training instances. This technique helps the model generalize better, as it forces to learn the hidden structure of the input rather than remembering the actual span context. The table shows the performance in predicting the correct labels using combination of the previously described techniques. 2 types of fine-tuning are reported. The first use all the textual content of the policies, while the second only use the paragraph that contains and this one rule. We observed that the combination of BERT plus data augmentation plus fine-tuning of rule text yield the best result in this case. Analyzing the performance of the overall system, thus after having constructed benefit rule by combining the predicted label with the ontology, we can observe that the fusion of the deep learning and rule-based approach yields the best F1 performance in respect to the structured rules. Another interesting aspect that can be observed from this table is that the combination of the 2 approaches reduce precision, but has a significant increase in terms of recall. In conclusion, we highlight that the policy enforcement is critical in ensuring that people can access the service they need. We demonstrated how AI and automation can shorten the rule from policy to code, and we have shown that combining deep learning and ontology can achieve best performance while providing interpretability. Thank you.